Right. Ready? So good morning all of you. Good morning, sir. The summary of the last lecture we have discussed this. Huh? Lattice vibrations. Sure. Okay. Right. So in the last class we have discussed this lattice vibrations, and just we have introduced the phonon or something like that. So what you have done? Oh, got it. Right. So we have discussed this 1D monoatomic lattice and a 1D diatomic lattice. 1D monoatomic lattice is not useful, not sensitive, and that's why we are using that a continuous structure. And we got two branches. One is acoustic, another is optical. And we have given a final table. So I hope for a number of atoms P, how many branches exist. Please go through that table. Okay, right. Take a fresh page and put the heading, thermal properties of solids. Thermal properties of solids. Thermal properties of solids. I have given 2-3 questions yesterday. Have you done that? Yes, sir. So thermal properties of solids. Ready? Stop. So here we are going to cover two properties. The first one, specific heats of solids. Specific heats of solids. Okay. Specific heat of solids. And the second one, thermal conductivity. Thermal conductivity. Here we will discuss Einstein model, Debye model. Here we will discuss Drude model, Lorentz-Drude model, that is for thermal conductivity. Okay, so here we are going to explain this specific heats of solids based on which one? Lattice vibrations. That means two contributions will be there, and today we are going to consider lattice vibrations contribution. What is the another contribution? Free electron contribution. Specific heats, two contributions will be there. One is the lattice vibration, another is a free electron. Lattice vibration proportional to T cube law and free electron proportional to T. That's why if you see the specific heats of solids formula, CV equal to A, capital A, T cube plus B, T. Not same. Oh. So A, capital A, T cube plus B, T. That is the formula for specific heats in solids. T cube law is for lattice vibrations and proportional to T is from free electron contribution. So the lattice vibration contribution. That means here we are neglecting the free electron contribution. Neglecting the free electron contribution. That's it. Okay, fine. So you are going to study what? Specific heats of solids. That too based on what topic? Lattice vibration. So first of all, let us see what is this a solid actually. Solid. The solid is nothing but a combination of atoms or molecules. You can take either atoms or molecules which are closely packed. Closely packed. Say yes or no? First let us discuss how they are packed closely. I already discussed somewhere else. Now if you consider the graph, whenever this is the force actually and this is the separation between the atoms. Whenever two atoms are very far away, which force is dominating? Attractive force. After coming to a short distance, that too equilibrium separation, repulsive force will be dominant. This is what we have discussed. So I think this is the attractive force and this will be the repulsive force. but the resultant force will be dominant at the mean position or equilibrium position. That's why the graph will be like this. This is the resultant force. I hope you have somewhere we have discussed. And this separation is nothing but what? Equilibrium separation. And that point is nothing but the equilibrium point. So finally, whenever, that means I am explaining how you got the solid again, because we are discussing about the lattice vibrations. What exactly lattice vibrations? Why those are called lattice vibrations? Now first, how that solid is formed. We have these atoms which are very far away, then the attractive force is dominant, that's why they are coming close to each other. After reaching equilibrium position, repulsive force is dominant, and that attractive and force and repulsive force both are equivalent or balanced. That means the atom gain which position? That means what? Your atom will stay at equilibrium position and oscillates. Is that clear? That means all these atoms are fixed to the lattice at equilibrium position and oscillates about that position. Since the atoms are fixed to lattice, that's why these vibrations are called lattice vibrations. 1 second. So that's it. So at equilibrium, we know the attractive force is equal to a repulsive force. That means atom is fixed to the lattice at which position? That's good. Equilibrium position and oscillates or vibrates, whatever it is, and vibrates. Since your atoms are fixed to the lattice, that's why these vibrations are called lattice vibrations. Lattice vibrations. That's it. Okay, so that's it. So finally, what do you understand? This is the lattice, for example. So in this lattice, our atom is at the equilibrium position. All atoms are at equilibrium positions, at which the repulsive force and attractive forces are equivalent, and they are oscillating about their mean position. Are you listening? They are oscillating about their mean position. Okay. So these oscillations are equivalent to harmonic oscillations. Repeat. Harmonic oscillations. That's good. That means all these oscillations we can treat it as just like a harmonic oscillator. This is the mass m and this is the force constant k, which is m omega square. According to quantum mechanics, the energy of the oscillator is equal to n plus a half h cross omega. That's it. So finally, I hope you understand what I am saying here. The first I explained how the solid is formed. Earlier also we discussed in the first class. So all the atoms are coming close together. At a particular point they stopped. That point is nothing but a equilibrium point. So your all atoms are fixed at the equilibrium point. Now you are in equilibrium, but you will oscillate. Not this one. So now you are oscillating about your mean position. Those oscillations are called lattice vibrations. And how to visualize these oscillations? It's simple. These are equivalent to harmonic oscillations. If it is a 1D harmonic oscillator, 2D harmonic, 3D 3D harmonic oscillator. Is that clear? Good. And okay, so whenever you are talking about the harmonic oscillations, you are getting some waves called elastic waves. Is that clear? And these elastic waves are having quanta of energy Could you please tell me what is the quanta of energy here? Phonons. Wait a minute. Okay, so no space. Come on, Ryder. So why these are called lattice vibrations? The atoms which are vibrating are fixed to the lattice point at equilibrium position. That's why these vibrations are called lattice vibrations. That's it. Then while you are doing the application, so which model we have to compare? You have to compare with the harmonic oscillators. If it is a one dimension, it is a combination of 1D oscillator. If it is a two dimension, it is a combination of two 1D oscillators. If it is a three dimension, combination of three 1D oscillators. That's why in Einstein model, you will multiply with the 3. Why you will multiply with the 3? 3 dimension, 3 oscillators. In 3 dimension, each atom is equivalent to 3 oscillators. If you want, I will write here. So the atoms are staying at the lattice sites or lattice points at their equilibrium position and vibrates. That's why these vibrations are called lattice vibrations. So each atom is equivalent to 3 oscillators in a 3-dimension lattice. And due to these harmonic oscillations, what waves we are getting? Elastic waves. So what is the quanta of energy of elastic waves? Phonon. Now ready. Ready? Right. Ready? Stop. Okay, so listen. Don't be confused with these two waves. One is elastic wave, another is EM wave. EM waves, quanta of energy is a photon. Elastic wave, quanta of energy is a phonon. So photon you know, already you are studying from long back. Now let us see what are the properties of phonon. Are you ready? So once again, which waves we have here? Right. If I say EM waves, that is related to photon. If I say elastic wave, that is related to phonon. Listen, very important. What is a phonon? It's a simply quanta of energy and a minimum amount of energy. Quanta of energy of elastic waves. That's nice. And what about its energy? Its energy E equal to same H cross omega, no change. I hope you know this is H cross. Omega can be written as 2 pi nu. Say yes or no? And what is this? Frequency. Babu, see the board. Frequency. That's why H cross 2 pi. I think frequency is nothing but velocity by lambda. Anything, whether light, sound, anything, velocity by lambda. So here velocity by lambda. Which velocity? Sound velocity. The velocity of sound. What is elastic wave? Okay, what is a phonon?
Quanta of energy in elastic.
Quanta of energy in elastic wave. What is the energy of phonon?
H cross 2 pi velocity of sound by lambda.
Okay. Elastic waves are longitudinal or transverse?
Longitude.
Why?
So, sound waves of
The velocity of sound. So that's why these are longitudinal. That's good. And I hope you know what is a 2 pi by lambda. 2 pi by lambda is equal to, that's why, listen, energy equal to H cross K, velocity of sound. Shall I write Vs? That's it. This is the energy of phonon, H cross K Vs. Say. H cross K Vs. In case of photon, what you will write? H cross K C. E equal to PC, P equal to H cross K, C. Okay. In the place of C, here you have velocity of sound. That's good. Very nice. Third one. Phonon spectrum. Phonon travels. Okay. Travels with velocity of sound. Next point. Phonon spectrum range. What kind of spectrum it is? The phonon spectrum range is 10 to the power of 4 hertz to 10 to the power of 12 hertz. What is the range of a phonon spectrum? 10 to the power of 4 hertz to 10 to the power of 12. Which region? Infrared region. Which region? Infrared. Molecular spectroscopy, we will discuss that spectrum, not here. That's it. And this is the phonon spectrum. Anything we left? Energy got, travels with velocity, and phonon spectrum is right. Good. Now here I have a doubt. This is the solid, and you are sending X-rays, and you are saying it is having lattice vibrations. You are saying, we can't see now. Are you observing? No vibrations. And you are saying there exist phonons. Okay. What made you to conclude there exist phonons? Means what experimental evidence confirming the existence of phonons? Interviews question they will ask. How can you say that phonons exist? If anybody asks, how can you say that photons exist? You will show him light. What is that light? Excitation of the electrons. That's why we are getting electromagnetic waves. That is nothing but photons. But he is asking, what is the experimental evidence to say that there exists a phonon? Anybody? Okay. So what is the experimental evidence? Ma very crucial, listen carefully for interviews. Experimental evidence of existence of phonons. Earlier CSIR top 10 students will go for another scholarship called Shyam Prasad Mukherjee scholarship. I don't know whether it is there or not right now. It is not there. Nowadays something PM scholarship, something, everything is on the name of PM only. Right. So earlier that was the scholarship. The advantage of that scholarship is earlier 18,000 was the stipend, 18,000. And with that scholarship you will get a 30,000. And contingency is also 1 lakh. Generally you will get contingency 30,000 or 50,000. Contingency and whatever the research work you are doing, paper, printing, pens, scales, lead pencils, all these things, so you can buy with that money. That is called contingency or something. Our student got all India top 10 rank or something like that. He went for that interview, Shyam Prasad Mukherjee, something. And they asked this. What is the difference between photon and phonon? Half an hour they questioned on that only. After that, of course, he didn't qualify. Ready? Right. So the experimental evidence for the existence of phonons. Two things are there. First one. Ready? Listen. First one is specific heat study. Specific heats of solids. Wait a minute. From the study of, Bob, everything is very useful for interview. Study of specific heats of solid. Actually, if you take the graph, I don't know how many of you seen, the specific heat graph, if you see, here the graph will be looking like this. This will be the graph. At a high temperature, it is a constant 3R. But as temperature decreases, the CV tending to 0. That means as temperature tending to 0, the CV is also tending to 0. So what they are saying is, as the temperature decreases, the specific heat is tending to 0. This is possible only when lattice vibrations are quantized. Because quantized means what? Only particular amount of energy is released or absorbed. For example, I have given 5 rupees to you, okay, and again you have given 5 rupees to me. How much you left with? 0. I have given 5 rupees to you, you have given 2.5. Every time you are not giving the proper one, you are giving half, something like that. Then what will happen? Finally you left with something. I don't know how many of you are understanding this point. So that's why this is a tending to 0 means absorbing, emission, or something like that, both are balancing, and finally you left with 0. This is possible only when lattice vibrations are quantized. Quantized. Please say this answer, that you will get full marks. That's good. This is one of the evidence. Next evidence, very important. Interaction of X-rays with solids. I told you earlier. So whenever you want to study the properties of solids, what you will do? You will send some X-rays. And you are sending X-rays. These X-rays are interacting with what? Lattice. In how many ways they will interact? 2 ways. One is elastic scattering, another is inelastic scattering. From that study, they confirmed that there exists a phonon. That how I will describe clearly. First write down. Properties of phonons and the experimental evidence. This is very, very, very crucial. I will explain more clearly. Oh, one more point I forgot. 1 minute. Phonon spin. Spin of phonon. Anybody? Spin of phonons. Very important question. Answer. 0 H cross. not 1 H cross. Photon spin is 1 H cross and phonon spin is 0. The reason is longitudinal waves. And that's why they obey which statistics? Bose-Einstein. So many blank faces are there while I am explaining all these properties. Maybe you didn't listen earlier. Be careful. Each and every point is very crucial for your set exams and interviews. At least now please remember. Phonon spectrum is which region? Infrared region. Frequency range 10 to the power of 4 Hertz to 10 to the power of 12 Hertz. And a phonon spin is a 0 H cross, the Bose-Einstein statistics. The reason why it is a 0 H cross, if anybody asks, it's a longitudinal wave. Photon is a transverse wave. Photon is a transverse wave and a phonon is a longitudinal wave. Second point we need to discuss, we need to elaborate more, but I won't give sentences, I will explain more clearly, but you please go and read from the book. How that interactions of X-rays with the solids confirm the existence of phonons. Let us see. Ready, Amma? Slow. Try to understand each and everything. Specific heats of solids, what is happening there? as the temperature is decreasing and the specific heat is also tending to 0. When you will get exactly 0 means whenever the amount of losing or amount of absorption, all these are quantized. Otherwise, you won't get exactly 0. So that confirms that the lattice vibrations must be quantized. And the next, interaction of X-rays with the solids. This is very important. Where Einstein theory failed? Here. According to Einstein theory, proportional to 1 by T, but according to Debye, it's a T cube law. Everything you will get. Ready? Are you ready? Stop. Amma, very important. Listen, please. Now here we are taking interaction of X-rays with the solids. Cool. So here we have two types of interactions. Means X-rays are scattered with the solids. Bragg reflection, Bragg scattered, something like that. Now the first one is elastic scattering. Elastic scattering. Listen please. What is meant by elastic scattering? The scattered photon is having same energy or different energy? Very few people are responding. Having same energy as which photon? Incident photon. So, for example, you have considered a lattice. Sir, photon or phonon? It's a photon. X-ray is what? Photon. X-ray photon. And we are studying the existence of phonons with the help of this scattering. Are you ready? What is meant by elastic? Scattered photon. Now I am assuming this is the lattice point and you are sending an incident beam with this. That is this is the X-ray incident and this is the incident direction. And it is scattered in this direction, I am assuming. That's why this is K prime. This is the incident, that's why it is K. Are you observing? Now, how can you confirm that there exists scattering in this direction? According to Bragg's law in reciprocal lattice, here you are having a valid reciprocal lattice point, and here also you have a valid reciprocal lattice point. I can take this is nothing but what? K, and if you combine these two, then only there exists a G bar. This is already we discussed. Say yes or no? So from this, what shall I write? Simply K bar, my important point is there. K bar plus a G bar equal to K prime. Although you are listening first time, I am explaining properly. Easily, slowly I am explaining. I am not using any difficult concepts. Try to understand. Maybe first time if you are listening, you feel little bit inconvenient. Quantum mechanics, every time, every year you have heard, every college they will teach. That's why you won't feel any unfamiliar. Scattering antadu, adenti, phonon antadu, what is this? First time you are listening, then you feel some inconvenience. Listen carefully. K bar, triangle of addition of vector, K bar plus G bar equal to, that's good. So I can take this K prime equal to, okay, already taken the same thing. Okay. K bar plus G bar. Okay, 1 minute. I think I can write it as a K bar equal to, come on, I say, a K prime minus G bar. Okay, so I can multiply with H cross on both sides. H cross K bar equal to H cross K prime minus H cross G bar. You know one thing, which is scattering? What is the meaning of elastic scattering? K magnitude must be equal to K prime magnitude. Say yes or no? So if I take the magnitude and these are equal, of course equal. Now I am asking, what is this term here? What you are saying? This is the momentum of incident photon. This is the momentum of scattered photon. Then what is this? All these things we are studying in which space? The entire crystal is represented by the reciprocal lattice vector G, and this indicates recoiled momentum, very important, recoiled momentum of lattice. Oh, the incident photon energy and the scattered photon energy same, but still there exists one extra momentum of lattice, and the lattice will be back scattered or simply recoiled. So this is not participating in any energy, but this term indicates what? Recoiled momentum of the lattice. We have already discussed earlier also. Hydrogen atom, it is emitting photon, then it will be what? Recoiled. In the same way, our lattice also will be recoiled. That recoiled momentum equal to, that minus means going back or something like that. Good. So that's why here any absorption of a phonon, any emission of a phonon, that means no absorption or emission of phonon, lattice vibrations, phonon. Sir, how do you know, sir? Array, if it is absorption, if it is absorbing or if it is emitting, how the energy of scattered photon and incident photon will be same. Is it clear? That's good. That's why this process is called N process. I don't know how many of you heard this name. Normal process. Scattering, elastic scattering process is called normal process, which is N process or normal process. Everybody understand this? Good. This is interesting. Now ready. So here we have inelastic scattering. Amma, this is very important. Inelastic scattering. Ready. So I hope you understand what is the meaning of inelastic scattering. The energy of a scattered photon definitely not equal to energy of incident photon. Why it is not equal? Common sense. It may be absorbing or it may be releasing some energy. So let us see what is absorbing and what is emitting. Okay, so here once again, energy of scattered photon, scattered X-ray photon is not. Are you listening? Don't place the hands. Photon is not equal to the energy of incident photon. So here we come across the two types of process. One is emission of something. Let us see what it is emitting. Emission. Another is absorption. All of you please listen. So emission. Now here I am considering the lattice. Every lattice is represented by a reciprocal lattice vector. What is that? G bar. That means whatever the interaction you are making with the reciprocal lattice, that will be referred to what? G bar. That is a reciprocal lattice vector. Now here this is the incident photon. That's why it is having a k bar. Say yes or no? This is the incident. Now it's a reflected. This is the scattered photon. That's why I'm taking as a k prime. Okay? So during this process, what is happening? The lattice will be disturbed and the lattice will emit phonons, because you know what is the amount of energy released or absorbed during the lattice vibrations? Phonon. Now let us suppose phonons are released. Are you observing? I am assuming this is the kph. pH for? I have not written anything for photon, but a phonon I have written photon pH. Is it okay? Good. Now ready. Incident. This is the k bar, and incidenting with the lattice, that is the g bar. That's why apply conservation of linear momentum. Initial, come on, say k plus g bar equal to k prime plus k bar pH. Say yes or no? Now this k prime equal to k bar plus g bar minus. So whatever the scattered momentum is less than the original or more than the original? Less than the original. Why? Emission. Okay. Next, come to this absorption. The same thing. I have taken a lattice which is represented by this lattice vector, reciprocal, and here it is a incident, k vector, and this is the scattered, k prime, and in this case it is absorbing, the same thing, k pH. Apply law of conservation of momentum. Come on, say k bar plus g bar equal to k prime. That's good. Now this implies your k prime equal to k plus g plus k. Now the energy of the scattered photon will be increased or decreased? Increased, because it is absorbing. Due to lattice vibrations, we are getting a phonon. That phonon is absorbed by this and it is going. Is that clear? That's why you are not seeing. You can ask one thing. It is emitting na. Here why you can't see? Virtual phonons. Virtual phonons. Okay, what is the meaning of virtual phonon? Really not exist. Just for our all these theoretical explanations, we are using all those concepts. Really does not exist. These are what are these? Virtual phonons. Ready? Wait a minute. Are you ready? How many vectors are here? Please count. That means more than 3 vectors are interacting. Say yes or no? More than 3 vectors. This process is called clap. Clap clap. You don't know. I heard that clap. Okay. So clap. Yes, sir, what is this? This is the German word. The German word. This is the German word. 1 second. German word which means flip over. English meaning is flip over. And the German word is unclap. That's why this inelastic scattering process is called unclap process. So if anybody asks what is unclap process means 3 or more vectors, interacting with the solid. But unfortunately, those are vectors, na? The combination of all those vectors never be equal to 0. It is always equal to G. It is always equal to G. That means because here 3 vectors are there. One is incident, scattered and phonon. These are vectors, na? If you take the algebraic sum, never be 0. Algebraic sum, never be 0. That is always equal to G bar. That process is called clap process. What is the meaning? Flip over. Flip over means what I am assuming I am saying. Maybe released, absorbed. Here the momentum direction is positive. Here the momentum direction is what? Negative. That means what is happening? The direction is reverse. That's why they named it as a flip over, something like that. But the English meaning is flip over, and the German word is umclap. Earlier I thought that unclap, not unclap. It's umclap, something like that. Is it clear? So this inelastic scattering is called U process. Which process? Or umclap process. Write down. The algebraic sum of 3 or more vectors never be equal to 0. It is always equal to reciprocal lattice vector G. Algebraic sum is not 0. It is always equal to the reciprocal lattice vector. Now if you want more information, please read the book. Diagrams also same as it is. They are given in the Wahab book. So please read. It will be very useful for your interviews. Clap process. I don't know exact pronunciation. You just find that exact pronunciation. Earlier I thought that unclap. It's not un, it's clap. The meaning is a flip over. Sometimes this is called a flip over process also. I think momentum vectors are reversed in the direction. That's why they said it is a flip over. Exactly, I don't know, but that is what I am thinking. 3 or more vectors interact with the solid in that unclap process, but the point is the algebraic sum never be 0, that is always equal to G bar. So the algebraic sum of the vectors in the inelastic scattering always equal to reciprocal lattice vector G bar. This year I am explaining all the things. Generally the last moment we will explain some questions and we will leave it, but we have plenty of time because we are taking morning extra 2 hours, no issue. I don't know how some other institutes will take only 3 or 4 months. I don't know how they are completing. We have to go and see. Maybe they will take more hours of classes, but I don't like. Teacher explained 4 hours means a student must work for 8 hours. Then only result will come, otherwise no. Just relax. The next phase what we are entering is very dangerous and very crucial. If you are not understanding the next part, you have to leave 2 things. One is the stat mech, another is the solid state physics. Your bad luck, both the same sir is explaining, that's why that is the bad luck. If 2 SARs are explaining, if you are not understanding in SSP, you will understand in SM. Okay? In stat, I won't explain again. That's the point what I want to say. So listen carefully. Anybody guess what common part is there between SM and SSP? Density of states. Here we call it the density of lattice points. There we call it as a density of states, nothing else. Just wait and see. So I hope you understand today what is a phonon. Actually what I have discussed for the last 1 hour, I think about phonon only. That means what are the characteristics of phonon and what is the experimental evidence. First one we didn't explain, maybe tomorrow we'll start Einstein model, Debye model, Dulong, Petit model, everything we will discuss. But the second one I explained, that interaction of X-rays, how to confirm the existence of a phonon. So why it is getting a different energy here? Because it may be absorbing or it may be emitting some energy. That energy who is giving? Lattice is giving. That lattice vibrations are giving. That's why definitely there exist the lattice vibrations, which quanta of lattice vibration is nothing but phonon. Just relax. Relax and don't sleep. I have seen one movie. So one patient went to doctor. The doctor is hypnotizing that person. So the doctor is saying, this patient, So you are going to you are going to deep sleep, something like that. Patient will be as it is, doctor will sleep. Patient is seeing as it is and a doctor slept. Also, you are understanding. I understood. Ready? Stop. Everyone, please see the board and focus. Very crucial. If you are not understanding this, you can't understand anything in the stat mech, Fermi energy, Fermi surface, Fermi energy level, nothing. All the things will be gone that you can enjoy there if you are not understanding this. That's why very crucial. Listen, what is the topic name? We have to give the apt name for SSP. So here we are going to discuss, take a fresh page, put the heading, density of lattice vibrations. Density of lattice vibrations. This is a very crucial. Debye model, Einstein model, everything, not Einstein model, Debye model based on this density of lattice vibrations. Listen carefully. Okay. So what is this density of lattice vibrations? So here we will get this topic in quantum mechanics or statistical mechanics as density of states. Density of states. First I will explain the quantum mechanics density of states. Stat mech or quantum mechanics both are same, density of states. Why we are taking this density of states and why we are taking the reciprocal lattice. First let me explain that and after that I will come back. Are you ready? Right, stop. So here I am taking one dimension. Babu, listen please. One dimension. One dimension means I can take 1D box. Exactly, no problem. So the wave function sin equal to under root 2 by L sin n pi x by L. I hope everybody know this n pi by L is nothing but k. In the derivation we got. Okay, so after that energy, that means energy En equal to n square pi square h cross square by 2m L square. Cool. Listen please. Okay, now I am considering first energies. What do you want? First, what do you want? I want density of states. Density of states. Sir, what is meant by density of states? Don't get tension. First I am explaining quantum mechanics, because if I explain with the help of 1D, 2D, 3D boxes, you will understand more easily. If I take lattice, that will radiate. Okay, ready. So density of states. What is the meaning of density of states? Number of states per unit energy. That's good. Babu, wherever I said number of states, in SSP you have to take number of lattice points. Per unit energy you can say, or per unit frequency also you can say. Because oscillations we are talking, that's why we will say for frequency. Understand? Number of states per unit energy. Wait a minute. Babu, I am taking first one small example. Are you listening? Yes. Now here, ready? Yeah? Here, from that wall to this wall, 40 feet actually it is. How much? 40 feet. And I placed some benches, one by one benches I kept. Each bench is 5 feet. How much? 5 feet. Total length? 40 feet. Each bench length? 5 feet. All benches are same length. Number of benches? 8. Huh? 8. You said very easily. And you need not to count the number of benches. If you know the total length and if you know length of each bench, you can say the number of benches. Say yes or no? Yes. Now, I have taken 40 feet. One bench 5 feet, another bench 4 feet, another bench 3 feet, another bench 1 feet, another bench 2 feet. How many number of benches are there? Can you say without counting? So I hope you understand one small example here. When you are able to say directly without counting, same lengths are there. Sir, why you can't count? I can't count 10 to the power of 23 atoms. Not only me, the whole world population sit together and count the number of Avogadro number of atoms. It takes their lifetime. It's not possible for counting that Avogadro number of atoms per cc. Adi per cc na bonda inkenni untayo, how many untayo? Are you understanding? That's why it's not possible for me to count the lattice point 1, 2, 3, 4 like that. That's why I'm searching for the alternate way. This is the best example. If you have total length 40 feet, each bench length is 5 feet. Without counting, you can say the number of benches is 8. Now see. Okay, now I am taking a real space first. Real space. Real space means energy space. Energy space. Babu listen. Okay, so this is the energy level or energy axis. You know what are the values of n? N equal to 1, 2, 3, so on. I am taking the points. N equal to 1, n equal to 2, 3, 4, something like this. Are you observing? Could you please tell me what is the first energy? Next energy? Next energy? Next energy? Now, you are finding the number of states. Means you are finding the number of points. Each point represent one state. Say yes or no? Now, can you count like this? Not possible. Let us suppose I have taken total length just like 40 feet. The problem is, could you please tell me what is the separation? అది కూడా సబ్ట్రాక్ట్ చేయలేరు, ఇలాంటి స్థితిలో ఉన్నారు. వాట్ ఈస్ ద సెపరేషన్? సెపరేషన్ నెక్స్ట్ 9. Are they equally spaced? Can you say the number of points without counting? No. That's why real space is not useful to find the density of states. Because the density of states means what? Number of states per unit energy. But still, you are not finding that one in the energy space. Why? Energy space is the real space, which is not equally spaced. Not equally spaced. Wait a minute. That's why we can't count. We can't find density of states. Okay, that's why we are moving to reciprocal lattice. If anybody asks why you are choosing the reciprocal lattice for finding the density of states, you have to say this: reciprocal lattice or space, whatever it is. In quantum, we will say space. In SSP, we will say it as a lattice. Okay, so since it is a one dimension, I am taking the k vector. K vector is equal to n pi by L. N equal to 1, 2, 3, so on. This n equal to 1 represent first state, ground state, first excited, second excited, everything. You know. Now I am taking k axis. Are you observing the board? Are you ready? Now, I am taking the k axis. So let us suppose here is a origin. Okay, this is the first point, n equal to 1, 2, 3, something like this, so on. and here also you can take, but wait a minute. Okay, so if it is n equal to 1, how much it is? Next, next, next. Now if you observe carefully, the spacing between these two is how much? This is spacing. That's nice. So finally what you are saying is all these points are equally spaced. Then what is the advantage? You need not to count one by one. Take the total length divided by spacing. Say yes or no? So that's why the number of states, again I will explain more clearly for SSP and SM. This is the main, what is this discussion actually? Why you are choosing the reciprocal lattice? I hope everybody understand what is the reason for that. The number of states equal to, now I am taking the total length. Shall I take the total length as a k? Because it's a k space. So total length by spacing. Could you please tell me what is the total length here? Now what is the spacing here? Pi by. That's it. Is that clear? Similarly 2 dimension, 3 dimension also we will take like this. So I hope everybody understand what is the importance of a reciprocal lattice, because the energy spacing is not same, not equal. That's why we can't find the number of states without counting. This is not possible. And if you take the reciprocal lattice space, all the points on the k axis are equally spaced. That's why if I take the total length, I know what is my lattice range or something, whatever I know, that k value divided by spacing, then I will get the number of states. In StatMech we will use the word number of states. In SSP we will use the number of lattice points. Come on. Just focus 1 hour. Again StatMech I won't explain. Please listen carefully. Please read the book. Please read the book. Next year onwards we are changing the strategy. That means just we tested for your batch how it works. Okay, it is working. June batch is a testing batch, December batch is a experiment batch. Student has to work more, not a teacher, student. Come on, come on. Length is k and the spacing is what? Pi by L. That's why the number of points or number of states equal to total length by spacing, because it is a one dimension. Ready? Yeah. Stop. Please listen. Now we are taking this one dimensional density of states or density of lattice vibrations. Everyone stop and see the board. Now I have taken k axis. It's an infinite axis. So somewhere you are having origin and that side you are having positive and this side you are having a negative. Until now what we have discussed is, whenever you are finding the number of points, here I am saying only number of points. If it is SSP, number of lattice points. If it is SM, number of states. Clear? Energy states. Just here I am saying a number of points. Just now you said the how to find this number of points or number of benches, which is equal to total length and luckily equi-space, that's why total length by spacing. Now I am taking the total length, some total length as a k, because it is a k axis, by spacing. What is the spacing? Say yes or no? Now this is the n equal to L by pi into, what is n there? Number of points, okay, but I can't take a number of states. I can't take a number of lattice points. I can't take a number of valid lattice points. I can't take a number of valid states. Why, sir? How you got this derivation? You have taken 1D box. Say yes or no? In 1D box, you have written that k equal to how much? Come on. Okay, n pi by L. This n value is what? Do you have any negative values? Say yes or no? That's it. For finding the number of states or number of lattice points, number of states or number of lattice points, your k never be negative. Because the k is n pi by L, that n is not negative, n is positive. Understand? So this must be, that's why k must be. But this is having both positive and negative. That's why out of this, how many are valid? How many are valid? That's why if you are seeing the textbooks, first they will write some number and multiply with 1 by 2, 1 by 4, 1 by 8, something like that. Okay. So I hope everybody understand. This 1 by 2 is for what? Valid number. The reason I have explained there. Now I hope everybody got n equal to L by 2 pi into k. Now I am taking two things. One is SSP, solid state physics. Another is SM, statistical mechanics. So here itself I am explaining side by side. Ready, Amma? In solid state physics, we call it as a number of lattice points. Number. This number is number of lattice points. Can you please tell me how much it is? N equal to L by 2 pi. I have given a heading, lattice vibrations. Check. Number of density of lattice vibrations. vibrations related to frequency or not? So that's why I don't want this k. So I hope everybody know velocity equal to how much? That implies k equal to how much? Cool. That implies dk equal to how much? Come on. That's it. Now I am finding the density of lattice vibrations, means dn. So dn equal to L by 2 pi constant into, now dk you know, dn equal to L by 2 pi d omega by, that implies the density of vibrations, lattice vibrations in the one dimension is equal to L by 2 pi into, that is the lattice, density of lattice vibrations in one dimension. Now this is the solid state physics part. Now onwards, everywhere you have to use this. V equal to k equal to dk equal to, don't forget. Next come to this stat mech. Amma important, babu important. सावधान से सुनिए. In StatMech, we will be having the density of states. And here this is density of lattice vibration. Ma, please listen, please listen. Good. Sir, again why you have taken 2, sir? Why you are creating trouble to us, sir? In StatMech, we have to find 2 cases. One is a non-relativistic case, another is the relativistic case. Here itself I am discussing because no time, that's why I don't want to discuss again and again in SM. So we have to find these 2 cases, density of states for non-relativistic electron, density of states for relativistic electron, relativistic Fermi gas, non-relativistic Fermi gas. That's why you have to use the density of states separately. Clear? Don't get tension, very easy, dead easy. Jujube, is it? Ready? Right. So density of states, already you got here, n equal to how much you got? Okay, no problem. dn, same differentiation. Come on, I say. I don't want this dk. What I am finding? Density of states, number of states per unit energy. I want in terms of energy. I hope, is it non-relativistic or relativistic? Non-relativistic energy equal to k equal to, any trouble? Now immediately I am finding a dk also. Earlier this one, remember, in case of SM, please remember in terms of energy and k relation. dk equal to under root 2m by h cross square 1 by 2 root e into, any trouble? It will continue for 2 dimension also, please remember, please remember. So k equal to under root 2m e by h cross, dk equal to under root 2m by h cross into 1 by 2 under root e de. Take it and substitute. dn equal to, are you listening? L by dk. Any doubts? And dn by dE. This is what? Density of states is proportional to how much? E raised to, for non-relativistic one dimension density of states proportional to e raised to minus 1 by 2. Any doubts here? Next, come to relativistic. dn never be changed, same as it is. First find dn. Come on, say dn equal to L by 2 pi into dk. But it is a relativistic. Energy E equal to how much? Relativistic energy E equal to Pc. M naught C square C, M naught square C power 4 is neglected. Come on. H cross K C. Okay. What do you want? K equal to? That implies dk equal to? Are you ready now? Now I am finding, this one. dn equal to L by 2 pi dk. Now dn by de, the density of states in one dimension for relativistic, how much? 1 by any energy term, that implies dn by de is proportional to energy power. Density of states, one dimension, relativistic case, independent of energy. One dimension, density of states, non-relativistic, proportional to e power minus 1 by 2. I hope everybody understand what is the difference between SSP and SM. SSP we are taking in terms of omega because vibrations, and here we need in terms of energy. That's why we are finding a relation between K and E. But bad luck, here non-relativistic case exists and relativistic case exists. Here no. Vibrations, no relativistic vibrations, no non-relativistic vibration. That's why the same thing will exist. Everybody understand? Come on. Please do it yourself, please. Take your time, but don't copy from the board. So here there is no energy, that's why it's proportional to energy power 0. Babu, please learn, please learn. Don't neglect. Up to 2014 we will explain this density of states in quantum. After that we changed. In quantum we don't have any applications. Actually at that time SSP I won't discuss. We thought that SSP SAR will discuss. SSP SAR is giving relations only. They won't explain what is this, what is this. So we change. Come on. don't copy, do it yourself. Same dn everywhere, but for SSP we will take the vibrations, that's why you have to rewrite k in terms of omega. And SM, whenever you are studying a Fermi gas, Bose gas, everywhere we will use this. Be careful. And in case of StatMech, we have to express k in terms of energy. That's why two types are there, relativistic and non-relativistic. Two cases. Density of states means don't think a density number of states per unit length to unit volume, unit energy. Careful. Length to area, volume will be here only. In 2 dimension, here you will get area. In 3 dimension, you will get volume. Now get ready for 2 dimension, make it fast. I will explain 2 dimension, 3 dimension diagram I will give, after that you please do it yourself 3 dimension. Ready? Ready? Right, stop. So here we are discussing this 2D. I will explain this, and 3D you have to do it yourself. Everyone please see the board. 2 dimension means what? Reciprocal lattice contains 2 axes, kx and ky. Remember, our k must be positive. It should not be negative. Am I right? Okay, wait a minute. Everyone see the board. I am taking this reciprocal lattice. This is the kx and this is ky. And I am taking the points pi by L, 2 pi by L and 3 pi by L, so on, 4 pi by L. Similarly, along y axis, pi by L, 2 pi by L and 3 pi by L, something like this. Now, I want to represent my ground state. It's a 2 dimension, 1 comma 1 if you remember. That means along kx1, along ky1, this is the ground state. Similarly, I will get the ground state first excited on all the states I will get. Each point represent one state. I hope you understand what I am saying. Good. Now if you join all these things, you will get something like this. So that means what? Your k space is spanned by. Your k space is spanned by. Spanned by. Spanned by what? Squares. What is this length? This one? Everywhere, everywhere. How much? Spanned by squares. What do you want to count? Number of lattice points or number of states. SSP will say number of lattice points, in SM will say number of states. Number of lattice points you want, am I right? Okay. I would like to find the number of lattice points per unit cell. Per unit cell means here it is what? A square. Your unit cell is square. Could you please tell me how many points are there in each square? Each square. That point is shared by how many? That's why sharing is. How many are there? Answer. Number of lattice points per square, how many? Now tell me, number of lattice points per square is 1. Means what? Number of lattice points is equal to number of squares. Say yes or no? That's why I can say number of lattice points is equal to number of squares. I can't count number of lattice points, but I can count number of squares by using geometry. Ready? So now I am going to find what? I am not finding number of points, I am finding number of squares by using geometry. Okay, so I am taking the symmetry. So with the origin I am taking the symmetry, and that means what? Along x and along y I am taking the same radius. That means what, you will get circular? Say yes or no? That's it. So because of symmetry I am taking this is the maximum possible k that my system have. In SM language we call it as a Fermi circle. If it is a 3-dimension Fermi sphere, that is the maximum possible k vector exists for the system. It depends upon the system to system. Is that clear? Wait. So this is the k. Are you understanding? Good. So sir, why you have taken circle? Why you are not taken square? I have to take equally in all the dimensions. Then what is the symmetry diagram? Circle. So if anybody asks, you can say symmetry. Ready? What I want? This entire circle is spanned by squares. Now I want to get number of squares. Common sense. See, this floor is having some area and some tiles are there. Let us say each tile is having same area. Then the number of tiles equal to total area by area of the tile. Number in the number of tiles equal to total area by earlier total length by length of the bench. Now total area by area of the bench. వీళ్ళని తీసుకొని కోటప్పకొండ తిరణాలకి వెళ్ళినట్టే ఉంటుంది CSIR ఎగ్జామ్ రాస్తే. బాగుందా? Number of squares equal to, రెడీయా, total area by area of square. Could you please tell me what is this length? This length area equal to, so total area by area of squares. Amma understand? Naaku doubt. N equal to number of squares equal to total area of this circle how much? Area of this square how much? Ready? Sure. So just to simplify, pi gets cancelled, L square by pi into k square. But I want number valid. You have considered throughout the circle, but here kx and ky both are positive, negative, positive, negative, negative, positive, negative. That's why this is not valid, this is not valid, this is not valid. Only 1/4 is valid. That's why, come on, 1/4 into L square by pi k square. Is it okay? So finally, n valid equal to how much? L square by 4 pi k square. Now here there is no space. First I will do here SSP, solid state physics. What do you want? Density of lattice vibrations. Ready? Now please take that n. Here n is the number of lattice points. N is come on. K square. Okay, now some textbooks will write pi k square by 2 pi by L whole square. Why they will write like this? Those are SSP, hardcore SSP fans. Because SSP is talking about always first Brillouin zone. First Brillouin zone length is 2 pi by L. That's why they will divide with 2 pi by L. But in SM we won't talk about Brillouin zones. That's why we have to talk separately like this. So no problem, both our answers are same, checked. So they will include that 2 in the Brillouin zone. That also same and no need to get tension. But careful, their formula contains 2 pi by L, our formula contains pi by L. Ready? So I would like to, yeah, come on. V equal to how much? K equal to? dk equal to? d omega by dv. Thanks. Now dn equal to, come on, L square by 4 pi into, I hope you are observing, dn equal to L square by 2 pi k dk. That means L square by 2 pi omega by v square. What is this? D. Any trouble, ma? Sure. And here L square is nothing but what? Area. 4 missing. Say. Ready. Now here I need not to explain. You have to do it yourself. So again 2 cases here. What is this? StatMech. Are you ready? StatMech. You please take a non-relativistic. I will explain this. Next one I want. Please listen carefully. Non-relativistic means you have to take the energy. Energy equal to h cross square k square by 2m. Come on. K equal to under root E root E. Come on. dk equal to how much? Okay, so now come on, take dn equal to L square by 4 pi 2k 2k dk. Ready? How much? 1 second. We want a 2k dk, na? We can do here easily. Why? It's a k square. If otherwise it takes so many steps, the small thing is find k square. K square equal to? What do you want? Differentiate. Okay, that's it. Otherwise you have to write many steps, ma. So dn equal to L square by 4 pi 2k dk. That implies dn by de equal to, come on, I say, L square by 4 pi into 2m by h cross. Don't change this 2m by h cross square. Keep it as it is. Any energy? That's why the density of states non-relativistic 2-dimension. dn by de is proportional to. Can you do the relativistic? Come on. So within the short time we can get both the SSP and SM. Please do like this only, no need to waste the time. Please substitute this k value and dk value. Here is k, here is dk. L square by 4 pi into 2 E by h cross c into dE by h cross c. And please tell me, in a non-relativistic 2 dimension is proportional to, I think you will get e power 1 here. But please simplify, I have written only that one. So h cross c whole square. So come on, you can write. don't copy, then you feel comfortable with the 3 dimension, you will do it yourself. Over. 2 dimension over. Start. K space is spanned by cubes. The number of lattice points per cube equal to 1. That's why the number of lattice points equal to nothing but number of cubes. I can't count the number of lattice points, but I can count the number of cubes by using geometry. The number of cubes equal to total volume by volume of the cube. Volume of the cube pi by L whole cube. Volume of the sphere 4/3 pi k cube. Come on, do it. And 1/8 why? Fraction. Only 1/8 part is a positive. Total how many portions will be there for a sphere? 8 portions. Front side 4, back side 4. Out of that only front side one portion is only kx, ky, kz positive. Remaining all at least one is negative. That's why 1 by 8. So all are positive, only 1 by 8. Just imagine a tennis ball, cut in the middle. Then you will get front portion half, back portion half. Again cut in the middle. Total 8 parts will be there. In that 8 part, only one part is a kx positive, ky positive, kz outward positive. If you take any other part, at least either kx or ky, kz will be negative. Come on. Be confident. This is very, very, very crucial for tomorrow's class. Debye model. Okay, can draw later. Come on, do it. My advice, just go for 1 week to home and come back if you want to clear CSIR. If it is not possible to study, please immediately come back. Don't waste the life. Only one time will get the chance. Generally, we won't study and we won't clear, and then we will say it is our fate. No, fate will be decided by our deeds. It will be decided by what you are doing. No one will decide. and I think this is L cube by, yes, 6 pi square k cube. Now we have to take this n again in SSP. That means L cube by 6 pi square k cube. We want to find dn. dn equal to L cube by I think 2 pi square k square dk. But we have to replace k equal to omega by v. That implies dk equal to d omega by v. If you take it and substitute, dn equal to L cube by 2 pi square k square omega square by v square into d omega by v. So, L cube by 2 pi square omega square by v cube d omega. This is tomorrow we are going to use this for a Debye model. Maybe after tomorrow, I think tomorrow we go to Einstein model. Okay, we can complete. So this is L square, you can L cube, you can take it as a volume by 2 pi square, and this is omega cube by v cube, where v is the velocity. Don't forget this. Here two modes will be there. One is the transverse mode, another is the longitudinal mode also will be there. We will do for both. That's why it will be split. That we will explain tomorrow. And for SM, this is a dn equal to same thing, L cube by 2 pi square k square dk, and you know what to substitute for non-relativistic. So k square equal to okay. So k equal to under root 2m e by h cross square. That implies dk equal to under root 2m by h cross square 1 by 2 root e de. If you take it and substitute, dn equal to L cube by 2 pi square into k square 2m by h cross square e into dk under root 2m by h cross square 1 by 2 root e de. So if you want to cancel, no, don't cancel, sorry. L cube is v by 2 pi square 2m by h cross square as it is, whole power 3 by 2 e power 1 by 2. Please check. This is a dn by de. I hope you got. This is v by 4 pi square, and this is a proportional to energy power 1 by 2. And relativistic, you know, E equal to Pc, which equal to h cross kc, and k equal to E by h cross c. That implies dk equal to de by h cross c. So if you substitute here, how much you got, amma? dn by de is a proportional to e power 2 or 1? 2. That's it. We are not only doing for SSP. While you are studying as a Fermi gas, Bose gas, everywhere, first we will start with the density of states. Without this, we can't find a single thing. Please do it, please do it. Don't write like this, complete the algebra. And for SSP, we have to remember this for a Debye model. In Debye model, we will use this. Any doubt? What? Any change? Omega? Omega square. Omega square. Is it okay? But today I request you please read about phonon spectrum. Phonon spectrum means lattice vibrations. How that X-rays are scattering, all these things. What is umclap process and a normal process. Umclap. So please read those things and don't neglect. Okay.